Hi, everyone. Thanks for being here. My name is Dong Song. I'm the founder and CEO of Oasis Labs, and I'm also a professor in computer science at UC Berkeley. So today, I'll introduce Nimble, a new approach to scaling, a new blockchain smart contract platform architecture that we have been developing at Oasis Labs that achieves much greater scalability than previous approaches. So today's computing, we face many challenges. We have untrusted infrastructure, untrusted applications, and also the applications may have undesirable data leakage. To address all these different issues at Oasis, we have been developing a comprehensive end-to-end solution, including a combination of different types of technologies, including scalable and verifiable smart contract execution, confidentiality preserving smart contract execution, and also at the application level, we provide privacy preserving analytics and machine learning. And overall, at Oasis, we're trying to build a privacy-first cloud computing on blockchain, which achieves a combination of a set of unique capabilities, including integrity for execution, immutability for the ledger, and also confidentiality in compute storage and the application layer for confidential smart contracts. We have done some earlier work from one of our research projects, Akiden, which talk about how we do confidential smart contracts. So in today's talk, I will mainly focus on the scalability aspects, where, again, at Oasis Labs, we are developing a new architecture for blockchain smart contracts platform to achieve greater scalability. So first, let's look at the evolution of blockchain and smart contract platform. So earlier, we have Bitcoin, which mainly handles, for example, payments and cryptocurrency transactions. And with the rise of Ethereum, we started having simple smart contracts. And then, as exemplified by CryptoKitty, we are seeing new and creative blockchain applications called dApps, on these blockchain smart contract platforms. And overall, essentially, we see an increasing trend for increase of the complexity of these smart contracts. And as a consequence, we also have seen increased congestion on these blockchain smart contract platforms. And in the future, we believe that we are going to essentially be running more complex and data-rich applications. And essentially, a lot of applications that people have been talking about in all these different application domains, including financial services, healthcare, decentralized exchange, and many others. All these applications, essentially, they all require more and more complex data and compute to support these applications. And this is one of the main bottlenecks of today's blockchain smart contract platform. And also, when we talk about scalability, it's important to note a distinction. So most of the conversations and discussions about scalability today focuses on what's called transaction throughput, like TPS. And also, most of this TPS focuses on simple transactions, like simple payment transactions. However, as I already mentioned, in the future, we are going to see more and more complex smart contracts and so on. And hence, scalability is not just about TPS for simple payment transactions. Scalability is more about how we can support these more complex smart contracts, both in terms of compute and also storage. So first, let's look at the scalability challenges for existing architecture. So for example, in today's Ethereum architecture, each node essentially does everything. Does execution, does consensus, and also does storage. So again, when we look at a blockchain smart contract platform, essentially there are three key functionalities that it needs to provide: the consensus, how different nodes reach agreements; compute, how to execute the smart contract; and storage, storing the data, including the state of the smart contract. And again, in most of today's blockchain smart contract architecture design, each node actually does all three functionalities all together. So they're all bundled together. And what's the consequence for this? The consequence for this is essentially every node has to perform the same work, including consensus, compute, and storage. So there's a lot of redundant and wasted work, and there's no parallelism. And poorly written contracts can negatively impact the network for everyone. So how can we do better? So with the Nimble approach, we propose a new paradigm. We call this separating execution from consensus. So essentially, we decouple these three key functionalities, consensus, compute, and storage, into each separate layers. And in this way, each layer can scale independently, and hence we can significantly improve the overall scalability of the whole platform. So again, with the separating execution from consensus, so we have different layers and different committees for doing these different functionalities. So with the compute, essentially we can have different compute committees to execute on the transactions. This can enable us to significantly enhance the parallelism, to increase compute capacity under heavy workloads, and support parallel processing better than other platforms. And the we can have compute committees for different transaction types, and it's very easy for us to support different types of runtime as well. So for example, in the Oasis network, we currently support both EVM, which is, so we are fully backwards compatible to Ethereum Solidity smart contract, and also we support a Rust-based smart contract language based on WASM. And also with the consensus, then the consensus committee agrees on the state transitions, which performs the consensus. And we use discrepancy detection to guarantee integrity of the computation results. And this approach actually allows us to achieve essentially much greater efficiency. We can have much smaller compute committee size than the traditional 3F+1, the BFT setting. And and then the consensus committee verify the state root hash to ensure that the committee reaches the consensus and keeps a immutable ledger. And again, by using this approach, separating execution from consensus, essentially, as I mentioned, we have these three independent layers, the consensus layer, the compute layer, and the storage layer. So I can quickly walk through the end-to-end workflow, how this approach works, and how this enables us to achieve greater scalability, in particular, to achieve greater scalability for more complex smart contract execution. So first, the user submits transactions, and the transactions are scheduled by the system scheduler. And this scheduler can also essentially try to have a good schedule that can reduce the conflicts between parallel transactions. And the compute workers are stateless. So at this point, we don't need any consensus. And the compute workers proactively execute the transactions, and the failure will have no effect on the actual state. And this allows us to have scheduling and compute to take place concurrently. And as a compute committees does a computation for a batch of transactions, then it will send the state changes, essentially the changes of the smart contract states, to the storage committee. And the storage committee also ensures there's a discrepancy detection to make sure that the compute committee also computes essentially the right computation results. And the root hash of the smart contract state, of the new smart contract state, will be then sent to the consensus committee. And again, at this point, the consensus committee actually verifies verifies the computation results are correct using a number of methods, including the discrepancy detection, and finalizes the state transactions. And also, essentially, the consensus committee also can make sure that the state has been persistent on the storage. So using this approach, we can have horizontal scaling to grow the platform with the usage. So compute, in this case, can be scaled as needed, so we can increase the number of compute committees to do parallel work as the workload increases. And also, as I mentioned, in this approach, we can easily support different types of transactions and also different types of runtime. And we use different approaches to achieve verifiable computing so that the consensus committee can verify that the computation results coming from the compute committee are correct. And one approach we use is using discrepancy detection, in the sense that we can detect, given a compute committee, as long as there's one node that is honest, any discrepancy that we essentially, we can detect any malicious behavior by detecting this discrepancy in the computation results. And we can use other methods for verifiable computing as well. And overall, this is the architecture for the Nimble approach that essentially goes through the different compute committees, storage committee, and the consensus committee. So this is the overall architecture and the Nimble approach for achieving greater scalability. In particular, how we can support more complex smart contract execution and greater parallelization, and also greater efficiency in the sense that by using methods such as a discrepancy detection, we can significantly reduce actually the size of the committee size, like the compute committee size, while achieving the same level of security. So now let me give you a few examples what this type of new approach enables us to do to support new applications that couldn't be supported by today's previous blockchain smart contract platform. So one example is a Kara application that has been built on top of the Oasis blockchain platform, this Nimble architecture. Kara is an application for essentially a tokenized data market for medical data. And the goal is to incentivize doctors and patients to share data and improve medical research. And how Kara works is using Kara, it enables patients to upload their medical data to the Oasis blockchain platform. And the data will be stored in an encrypted form. And using the confidential smart contract capability that's provided by the Oasis platform, a medical researcher can write a privacy-preserving smart contract, and which enables the medical researcher to train a machine learning model in a privacy-preserving way, utilizing patients' medical data. And also, the smart contract can specify how users may get compensated and can write. And as medical researchers using this approach to train machine learning models in a privacy-preserving way, it can then test, for example, the effectiveness of the trained machine learning model, and users may get compensated if, for example, the trained model generates some profits. Or in certain cases, the patients are just very happy to contribute their data in a privacy-preserving way for medical research. And you can read about some articles about this project online. So that's one example, the carrot example. In the carrot example, essentially the data is uploaded to the Oasis blockchain platform, and using privacy-preserving data analytics and machine learning capabilities, it enables medical researchers to train machine learning models in a privacy-preserving way to help them essentially try to find better cures for diseases. And also recently, we have been developing another approach that we call decentralized federated learning, HiveMind. Using HiveMind, each device, each user gets to maintain their data locally, and then we use a smart contract to coordinate federated learning across these different devices, so that without uploading data to the cloud or to a blockchain platform, this can actually enable also different devices and different users to collectively build machine learning models, also in a privacy-preserving way. And we are experimenting with this approach as well. And these are all examples of how essentially to support these type of more complex applications, you need to be able to support much greater scalability for this more complex smart contracts. And there are many other examples of applications that will require these complex, more complex types of smart contracts, ranging from DeFi, IoT, to supply chain, and many others. And so we hope that the Nimble approach can really, for the first time, enable many applications in these domains, given its advantage in scalability properties. And recently, we just released our DevNet 2.0 and the Oasis SDK, which has a number of new capabilities and features, and includes also much better developer experience. And we welcome everyone to check it out. And to start building on Oasis, please sign up at dashboard.oasiscloud.io. And in later Q3 and Q4, we will start our bug bounty to invite the community to help us to find bugs and try out our system. And also we'll be launching a public testnet and also with a staking competition. With that, we invite everyone here to develop on Oasis and to run a node on Oasis. And for more information, please go to oasis-protocol.org. Thank you.